I'm really happy to be able to talk with Paul today about his experiences using spaced repetition to learn mathematics. For those of you who don't know, Paul is a mathematician from Quebec, and he's been using spaced repetition to learn mathematics for an exceedingly long period of time. How long is it altogether, actually, Paul?
Um, Space repetition, I think 6 months and a half, a little bit more, and 6 years and a half.
Mm,
And for mathematics itself, maybe 6 years or 5 years and a half.
wow.
I'm not too sure about the exact numbers.
Beautiful. So could you take us like right back to the beginning? Like, how did you learn about using spatial repetition? Because it's quite a niche topic. Obviously, for certain domains like language learning, it's become quite prevalent. But for mathematics, like I was saying it earlier before we started recording, there's not that much information specifically about using spatial repetition for mathematics. So how did you come across it?
Okay, so something like 7 years ago, I was interested in learning about learning. So I got a few books on the topic, and I think one of first is called How We Learn:
Mm,
The Surprising Truth About When, Where, and Why It Happens by Benedict Carey. And on it, he mentioned space repetition, and at some point, I found about Piotr's website. And I was instantly hooked on the topic. And I
mm,
started first to learn about standard vocabulary, but I kept thinking there must be a way to learn math, but without the LaTeX plugin, I didn't know how to do it with SuperMemo.
mm.
I was not able to learn any kind of advanced math. But at some point, a person told me about Enki, and then I discovered that there were software with LaTeX, and that's how I learned about space repetition. And
Okay, okay. So were you already quite advanced at math by the time you'd started using spaced repetition?
yes, I already had a PhD. No, sorry, I already had a bachelor in math.
Okay,
I was doing at the time a PhD in theoretical computer science.
okay.
Uh, so I already had lots of knowledge in math, and it was helpful uh, because I might know where the particular answer to a particular question is, even if I don't recall everything.
Mm. So one of the things that really interested me about the discussion we did a couple of months ago, where you talked about both your experiences learning mathematics and also learning Stoicism as well, you mentioned that you'd sort of developed your own system. It really is kind of like a system or method for learning mathematics. Could you sort of briefly give like a general introduction to your method of learning math knowledge with spaced repetition?
Very well. First, a lot of it I consider is just an application of Piotr's ideas on flashcard formulation,
Mm,
and the the essence is that your questions need. Um, Sorry, let me talk about the kind of statement that there are in math that we might be interested in learning.
mm,
In mathematics, at the most fundamental level, there exist three kinds of statement. One is axioms.
mm,
So an axiom is just a statement that you take as true. Then there exists definition,
mm,
and finally there exist theorems and their proof. And a definition, in some sense, is a chunk. So when I say that an object is a group, for example, I'm saying that it has a certain list of properties. I converted a huge list of properties into a short, meaningful thing. Uh, we already see a link with the psychology. In psychology, we can of learning. We know that to learn more and more complex concepts, uh, we have to chunk. We have to regroup things in a meaningful way. And finally, there are theorems and their proof. And there's really uh, nothing. A theorem is merely a statement that is true, and that has a proof, and the proof is just a sequence of statements that lead to the fact that the theorem is true. And so my general method is that I learn axioms by just asking standard question about them, like can you state the axiom of choice, or
Mm.
I learned group theory just by making a clause deletion. And for example, learning what is a group, I will say G is a group if, and then there's a list of things like it has a binary association. The operation is associative. There exists a neutral element and there exists an inverse. So it's just like memorizing a standard list. And finally, I memorize proof by closing the theorem. And when it's time for the proof, I just memorize it line by line. But the important thing is that each line of the proof need to be either something that has been proven previously, or a very trivial application of it, or the application of rules of inference that I've already mastered. And that's about the idea. So I would not say I'm doing anything new.
Mm.
It's just that there's a set of skills that need to be learned, uh, and that are not learned usually in mathematics. One is to have a proof that are much simpler than usual.
Okay, okay. So it seems like when you're learning axioms and definitions, this is very similar to most of the other kinds of learning that people do with spaced repetition. It sounds very similar to sort of vocabulary learning with language learning, or just like learning history with spaced repetition. There's not that much that's different, but it really does seem like there's kind of a difference with the way you learn theorems with, like proofs and theorems with spaced repetition. So could you go a little bit deeper into specifically how you go about learning proofs? Because I think one of the difficulties is that proofs are very similar to sort of long lists of items, like enumerations. And anyone who's read, obviously, the 20 Rules for Item Formulation by Piotr knows that enumerations and lists are like the number one thing that are really hard to encode as items, and they often end up being leeches or lapses or whatever. So how do you go about actually creating, how do you go about formulating a theorem that can be turned into atomic flashcards?
So if let me just think about this one. Let me talk a little bit about what is a proof
Mm.
first. So in math, if you start with logic, a proof start with a few elementary statements that are called axioms, and a bunch of rules of inference. For example, if in my proof there's the statement P, and then there's the statement P implies Q, I have the right to write in the next line Q.
Mm.
And this is a very, very simple rule of inference. And it might not look like it in mathematics, but every proof, if you were to write it down in using a logical language and completely unpack it, it would at every step use rules that are that simple.
Mm.
In the same, so the way I do it is by using very, very simple rules of inference, and also by doing a lot of chunking, where I increase my numbers of rules of inference. Let me try to give an example. There exist rules of inference that are more useful than other rules of inference.
Mm.
For example, if you start with the rules of natural deductions, and you consider a law like De Morgan's law that say that the negation of P or Q is equal to the negation of P and the negation of Q. If you add this rule of inference into your proof system, this will shorten your proof, all your proof, because it's a statement that you use all the time. So a lot of it is about finding statements that recur a lot, and rules of inference that are kind of like useful to add to the huge collection of knowledge that you do have in such a way that the proof get all your proofs get simplified. So the way you write simple proofs is by having lots and lots of rules of inference that have great applicability.
Very interesting. Okay, so I'm going to try and having listened to that, I'm going to try and sort of explain how I think of it, and I'm going to ask you whether it's correct, because I kind of want to give a almost like an analogy for perhaps people who are just starting out learning math like me, or just someone who isn't really familiar with mathematics. So when you're talking about building up, sort of you're sort of talking about building up larger rules of inference that can form sort of larger reasoning steps, larger reasoning
Yes.
shortcuts from more fundamental reasoning rules, basically.
Yes.
So to sort of make it, this is how I think of it. I think of it like natural language. If you imagine, you can have like a sentence like the person who teaches students, and that sentence can be represented by a smaller chunk, just the noun teacher, because they're a person who teaches students. And then you can replace that longer sentence with a much shorter sentence, teacher, and it's like you have this reasoning shortcut. So that's essentially what you're doing when you're reusing, for example, theorems that you've already proved, or you're using larger like rules of inference built from smaller ones. It's like yeah, just like you said, like chunking, I guess.
Chunking occur more often in definitions.
Mm.
So a definition is really a chunk, but when you, I would not say necessarily that a theorem is a chunk. For example, De Morgan's law replaced two. I'll keep using that example. The negation of P or Q is equal to the negation of P and the negation of Q. This is not necessarily shorter, but it's just very reusable. It's a
Mm.
pattern that comes often, and by adding rules that come often, you don't have to reprove everything twice or three times or four times.
I'm reminded of a quote I read the other day in one of Woz's articles. It was like, you know, intelligence can be split into a bunch of different components, and one is like the amount of general knowledge you have. But the more important one that Woz stresses is having, being able to think in abstract terms and having these very abstract and applicable rules of inference that you can reuse in lots of different areas. So is that sort of the benefit?
Yes, okay, so that's an important part. You want the rules of inference, your rules that allow you to go from one statement to another to be as general as possible, because that allow you to reuse them a lot. To give an example to people here, if I say that 2 plus 3 is equal to 3 plus 2, it's not as useful as a bit of knowledge as knowing that for any pairs of natural numbers m and n, m plus n is equal to n plus m.
Mm.
So one deserves to be memorized because you will use that thousands of times in your life, while the other is much less important. So we are looking for the concepts that get the most reuse. And Stephen Wolfram wrote a post about that where he found out that a lot of things that mathematicians consider important enough to write in a theorem in a book are the statements that have the greatest ability to prove other statements.
Mm. Very interesting. So, um, you know, from my cursory knowledge of mathematics and having looked through like a couple of math textbooks, it seems like the proofs tend to be really long, right? So,
Yes.
how do you go about turning something that's really long into something that's short enough to be like turned into flashcards?
Okay. So you say they tend to be really long, but they could also be even worse in the sense that they are made for people who are not using spaced repetition. They're made for people who have a pen, paper, and pencil, and these. But they still cannot be super long because else even your memory would fail you. So they already have to incorporate some simplification and some chunking. It's just that you exaggerate the process. If a proof in a manual is 1 page long, it can always be decomposed into lemmas and sub-lemmas and sub-sub-lemmas. And what you do is you take a proof that depend on many complex statements, and you find what are these big statements.
Mm.
And one thing you have to do, absolutely, is you can't just cut and paste the proof you find in the manual. It will be way too complex for space repetition. In space repetitions, when one line of a proof should be a super simple rule of inference, and the proof should be super short, else you will feel overwhelmed by the complexity. You won't be able to compute it in your head. And one thing that I find very important is to have way more definitions and way more theorems than you would naturally see in a textbook. For example, I was working recently on a proof that the Kolmogorov complexity function is uncomputable, and in a textbook, they will not add as much definition as I do. I might add a definition for the proof and for the context of the proof. Instead of introducing a function f that I will completely forget about, I might give a very salient name to that function f. And I will make a flashcard that define this function with that name. What is it? And then I will remember it outside of the context of the proof. And you have to do that. Basically, you have to make every portion of the proof able to stand alone on its own, where you're able to unpack every part of the statement in your head, where every part of the proof needs to come from a rule of inference that you already master, and it can be done. I'll just give an analogy. The most you do coding, right?
Yeah.
Okay, so if I have a super complicated program, I could probably simplify it into a bunch of sub-function. I could have an algorithm that has several parts, and I could give meaningful name to these parts, and these sub-parts could be decomposed themselves into sub-functions and sub-sub-function up to the point where you arrive at the elementary operations of computers.
Exactly, yeah. Very
And
interesting.
it can be done.
So would it be okay to show some examples of cards? I think it would really help with people trying to understand.
So this was a random flashcard. I'll give a complete example. Let me give you another one. This was a former leash, and I'm proud to say that it's no longer a leash. What I'm going to show you. So it's a proof that the Kolmogorov complexity is not a total computable function. And as for memorizing the statement, it's really hard to close that statement. But if you've memorized the proof, you will instantly know that just by having done the proof, I will instantly know that the statement is true because the proof flashes in my mind. And the proof has 1, 2, 3, 4, 5, 6 line. It's a super short proof, as you can see. And it's a proof by contradiction. So I suppose that it is total computable. And then the next line of the proof is that another function that I call berry_comp is total computable. And I made a flashcard that says that if Kolmogorov is total computable, then berry_comp is total computable. And I memorized the implication, and I memorized the proof of that implication. So I memorized in another flashcard that if Kolmogorov is total computable, berry_comp is total computable. So I already know that. Then the third line is an application of what's called the clean recursion theorem. And I already have a flashcard that say that if there exists if a function is total computable, in that case, if a function is total computable, then there exists an x such that universal of x is equal to f of x for the function that is total computable. So it's just an instantiation of a rule that I already know. So this one is just an application of a theorem. I know that theorem by heart. And then there's two other statements that I prove separately, that Kolmogorov of universal of x is lower and equal to the length of x, and Kolmogorov of barrier of Compte is greater than x. And then I've obtained that these two quantities are equal, yet one has a length lower or equal than the length of x, and then the other has a length greater than x. So I've obtained a contradiction, and poof, Kolmogorov complexity is therefore not total computable. It's not important for the people who are seeing this to know theoretical computer science, but all I want to say is that I've used only very simple rules of inference, and it was not presented as simply as that when I first saw the proof.
Very interesting. Okay, so just to go back really to the basics. So this first picture that you posted, is that like the question side that you see when it pops up?
Okay. Yeah, that's the question side. And the way I do them, so the first one I posted, it's just a proof that sin of x is equal to the imaginary part of e to the power of ix. And there's a bunch of things. So this is the statement itself. And generally, I have to scroll down to see the proof. This way, because all these clauses are linked in Mnemosyne, I never want to see the lines that come afterward in a proof. I never. I always want to. And when I look just at the statement, I don't want to see the proof. So that's a bit weird
Okay.
for a criminal user.
No, I understand now. I understand. So what you see is at the top, you see like an assumption. Do you ever have more than one assumption? Like right in the first picture, you have let x is a real number or whatever. Would you have multiple?
Yeah.
Okay. And then
but you don't want too many assumptions. At some point, you want to chunk your assumptions.
Okay. And then you can see it says proof, and then you're allowed to scroll down until you see the close thing, and then you have to answer what's in the close.
Yes.
Understood.
So, and sometimes it's the statement itself that is closed. So I close part of the statement when it's possible, and I always close the proof. And there's another thing I started doing recently. It's that after each new flashcard I create, I type a bunch of random numbers and letters. And if I do a subproof, I copy paste these random numbers and letters, so that this way I can easily find all related flashcards.
Okay. Could you give an example of that?
Oh, yes, I will for the Kolmogorov function. So, okay. You can see there's a bunch of random letters at the end.
Yes.
Now I'm just going to show you another flashcard, and it's really easy for me to find them. So this is another statement related.
Okay, and so you've pasted in the same sequence of characters at the end.
Yes.
And so this is like a sort of is it completely manual? Like you just make up the random numbers yourself, or is there some?
Yes.
Okay.
Yes. And seriously, it helps a lot.
Okay. And so this is like sort of a manual way of doing. I think someone mentioned in the chat. Bit for brains. So this is the random numbers, almost like a Zettelkasten type sort of internal link. If you're familiar with that.
I don't know Zettelkasten type internal links.
Okay.
But the goal is just to be able to quickly, if I have a proof, I quickly want to find the substatement, and sometimes I want to delete some because they're no longer useful once I've changed the proof, or sometimes it's even to link a statement to another. So I started doing this, and I really like it.
Very interesting. Yeah. Is it a lot of work to do this? It seems like
No.
Okay.
Okay. Here's the general process. Whenever I do a proof, every time there's like something I want to simplify, I just start with a copy and paste, and it's a copy and paste. It's not a lot of work.
Very nice. Yeah, this is really cool. So, are all of your cards, are they all closed cards? Or do you
Yeah.
have some Q&As as well?
I started with Q&A at some point, but the truth is a Q&A is can be done with a close, so I just use closes.
I'm the same, yeah. They're just quicker.
Yeah.
Oh, and also, how do you deal with like conflicts of symbols?
Oh, yes. So you do it by starting to differentiate your symbols. To give an example of symbol differentiation, um, I might say I type I might talk about the natural number greater than zero or the natural number greater or equal than zero by adding little symbols on it. So you can add more symbol. You can start using different symbols. You don't want a conflict of symbols because in ordinary mathematics, you already know the context. But in space repetition, you navigate from context to context so quickly that you should be able to look at a symbol and know instantaneously what it means.
Mm.
Uh, and you, the worst thing you could write is stuff like what is the function f equal to? I don't know what the function f is because it's used for so many different things. So that's why you want to give very meaningful names to your function.
Okay, so that's like the berry comp thing. That's like a
Yes,
example of a
yes.
name that you've just made up.
Yeah, it's a name I just made up because before it was a leash because I called it the function f and that I gave the definition of f, but then I got all mixed up. But now when you talk about the Berry-Comp function, of course I know what it is.
Okay, does this make it difficult to communicate with other mathematicians if you start talking about berry comps? Do they just
I
look at you
would
like you're
never.
crazy?
Okay, the thing is, I would never talk about the Berry-Comp function to other mathematicians.
Mm, mm.
I would tell them what the function do,
Okay,
and then I'm no longer a crazy person.
okay. Okay. Yeah, someone mentioned in the chat this does look quite similar, I guess, to neural linking. You're creating links between these between all of these related proofs and theorems and things. Do you ever do like subset reviews of a given theorem to try and when you're problem solving perhaps or researching
Um,
a topic?
no, because all the theorems are always clearly in my head with high recall. So
Okay, so you don't find it really necessary to do it.
no, and there's
Okay.
not that option in Mnemosyne.
Okay. Do you have any cards where there's like additional context in like in a field, like perhaps in parentheses you put like, I don't know, the history of why this thing is useful, or maybe some intuition, like maybe not just formal statements, you put like some intuition about a given theorem or definition.
Yeah, yeah. Let me give you one because that might be interesting.
Mm.
We will continue with the same example. Do you see what I just sent?
Yes.
So this was part of the same sequence. The Berry-Comp function, what is it? I have both the formal definition and this one is like with lots of words.
Okay.
I did both. It's rare I do that, but I really wanted not just the formal statement, but a clear, intuitive understanding of what's going on. And
Okay.
sometimes, most of the time, it's not necessary. But this one I found a bit tricky, and I added both a formal proof and an intuitive proof of some of the statements. In general, I have super formal proof, but for this one that I found a bit tricky, decided to add the intuitive explanations.
Okay. And so do you usually find that's not really necessary? You prefer to keep things formal, or do you often add this sort of intuition?
It's the only. It's very funny you ask this because it's the only proof where I have an intuitive explanation.
Oh, really? Okay.
Yes, yes, and it's because it caused me some troubles for various reasons. So,
Oh,
uh,
interesting. Oh, that reminds me. I was reading as I think in the last event you mentioned that there was a paper by Leslie Lampard that was very
Yes.
important to sort of the development of this method that you use. And Leslie Lampard, for those of you who don't know, he wrote a paper called How to Write a Proof, and he's actually published a new version of it, I think in 2012. The original one was from like the 1990s. And yeah, could you sort of explain why that paper is important and sort of the ideas that it gave you that led you to develop this method?
Um, so I'm not even sure if the ideas themselves led me to develop the method. It's just that I realized that the method I was used was already used in this paper.
Okay. So you'd already
But
had your method.
I don't even recall, but I don't even think I read the paper.
Okay.
Or I read a few pages and it okay, but let me explain the paper. In the paper, Leslie Lamport says that most proofs are too complex and that they should be decomposed into substatement and sub-substatement up to the point where each statement is extremely elementary. But in the case of Leslie Lamport, he wanted that for ordinary mathematical writing. So his suggestion is that in ordinary mathematical writing, you should do that, and he says it makes the proof clearer.
Mm.
And it is certainly the case for spaced repetition that you have to do that. There's no uh, there's no choice. It's really the only way. And the reason I recommended the paper is because it gives a clear explanation of the steps to do to decompose a proof, and it gives many examples. So for people that are interested in learning that, I recommend reading the paper. Uh, but I don't even remember whether I was inspired or not because I think that's the only way to do, and it should be the
Yeah,
at least for spaced repetitions. And it
yes.
happened rather naturally because the truth is that my early proof were very complicated
Mm.
and they led to leashes. And then at some point, I started decomposing the thing into sub statement and shorter sub statement until the point where my proof were all very short and very few lines. Like when I started, I think I had a proof with 20 lines, and it works for the first week, but at some point it starts to really break down in your mind. Like you no longer remember what you're doing.
Yes, exactly. Yeah. I mentioned him because he right at the beginning of the paper I've made it like halfway through I think so far, and he's really criticizing sort of the essay style of writing a proof because it's imprecise, it's easy to make errors. And he's sort of talking about it in the context of doing like mathematical research or whatever. But it's also very important, obviously, for spaced repetition because you need to, as you just said, you need to keep things short, you need to keep things concise, so that you can create atomic flashcards, which are important. Like they're just an important thing to be able to remember something. Um, all right, so I think at this point, uh, I realized I didn't make it very far through all of these questions. There were so many good questions that people were asking. But I bet there are people right now, like listening to the event, who have questions, who want to ask them. So I guess I can open it up. If someone's got a question, um, feel free to just unmute yourself and go ahead. And oh, just a reminder that everything's being recorded. So if you don't want to be recorded, post your question in the general voice and I can read it out for you. So yeah, go ahead if anyone's got a question.
How do you mentioned like you have names for like sub statements in a proof that wouldn't necessarily be a formal theorem in the book or the paper, and you gave an example of one of the names, the Berry comp. Do you have a system for choosing names? Because I could imagine if you name statements poorly, you're then kind of just adding load of like something else you need to memorize rather than something that's intuitive.
Um, I don't think there is a system for naming things, but you're right that the names should be intuitive. And there's a reason why I called it the Berry-Comp function here. It's because it's related to something called the Berry paradox. And this function is completely related to Berry's paradox. So that's why I call it the Berry-Comp function. So of course, you want the thing, the symbols to be meaningful and to be related to other images and names in your head. But I don't think there's a system for naming things. Not anymore that there's a system for naming things in real life. There's lots of way people go about it, but of course, a good name should activate something in your head.
Is it kind of like a mnemonic in a sense?
I guess so. It's something that a good name should be intuitively clear,
Hmm.
but I don't think there's a formal way of generating good names.
Very nice. Oh, there's a good question from Bit for Brains. Do you use images in your cards?
I wish.
Oh, you wish? You don't use them?
I wish, but well, I realized that for my category theory, there's no choice but to use a better image. I can't just use the standard LaTeX, and I need to use LaTeX to create the diagrams.
Mm.
There exists field of mathematics where I realized after many years that you can't just learn line by line. A diagram might be clearer than a line, and one of these fields is category theory. I need to learn how to make images. That's one of my goals, like for this year.
Oh, cool. Oh, that's really interesting. So that's
Or
that's for like category theory you mentioned is an area of mathematics where the diagrams are really useful and important. Um, are there any times where you use diagrams to give you sort of a geometric intuition where it's not necessary? It's just
in
because
my
it
case,
gives you a better sense.
I don't do a lot of geometry, so no.
Okay.
But I do think for people that study geometry, having drawings might help. And another field where it's absolutely important to do drawings is graph theory.
Mm.
I could, in theory, describe a graph by giving the list of its edge, but it's not and vertices, but it's not as easy to memorize as just the image in many cases.
Okay, that makes sense. Okay, Nitro's has got a very good question that I forgot to ask. Um, how do you practice problem solving, and how do you schedule problems and like work with those with inside the space repetition system?
Um, that's a cool question in the sense that problem solving is something people do at school where they have a manual and there's a list of problems. But in reality, all these problems are about proving theorems. So it's the same standard method. If there's a theorem that I want to prove because I think it's interesting and I think I might have a proof, I will practice it using normal pen and I will try to solve it using my brain and pen of paper, and then I will note the proof in the space repetition system. So the answer is that I first have to solve the problem and then I remember the steps.
Okay, okay. So you don't put problems that you want to solve inside the space repetition system. You put problems that you've already solved in there.
Yes.
Okay. And so how do you balance like could you like take us through like a day in the life of Paul? Like how do you split up your space repetition learning from your like working on problems on paper learning?
Um, it's vary from day to day, but
Mm.
often uh, there's like a statement that will really interest me, and I might start researching it on Wikipedia and thinking about it, and then doing maybe the proof already exists somewhere. Then it's easy. I just have to copy and paste it, or I you have to solve it in a normal traditional way, like a normal traditional mathematician. The fun and the space repetition fun begins afterwards. Once you've solved it, then I write the proof, and the magic happens like afterward when I'm doing the repetition. Often I'll think, oh, or when I write it down, often I'll see a way to simplify and to simplify and to simplify. Uh,
Mm.
I think we work on a very simple problem together uh, recently about set theory.
Yes, yeah.
You came with a statement that you wanted to prove.
Mm.
The fact that the empty set is different from the set that contained the empty set itself. And
Exactly.
while writing down the proof, uh, I realized that there was an intermediary statement. And let me tell you something funny about that intermediary statement. In my space repetition flashcard, I had to use that rule twice today. The fact that if a
Oh,
set is not empty, then there exists, then it's true if only if there exists an element inside it.
that's awesome.
So for the people that are here, James uh, was learning set theory, and he wanted to prove that the empty set is different from the set that contained the empty set. And in set theory, there's an axiom called the axiom of extensionality that state that two sets are equal precisely whenever they contain the same elements. And there's another axiom that says that there exists a set that is the empty set, and that set contains nothing. And by using the axiom of extensionality and the axiom of the empty set, we can find out that if a set contains an element, then it's not the empty set.
Exactly.
And
Yeah. I was really trying to prepare for this talk, so I was trying to boost up my proving skills. That unfortunately, I'm still not very good at mathematics. But me and Paul, we actually want to do like perhaps in the future, like a series of videos where either it's me learning and he's like watching me commentating or giving me tips while I try to prove something or try to reformulate what I've already created in a space repetition system. Or the other way around when he's learning and I'm asking him questions, because I think it would be really useful to have that sort of that pairing between the complete beginner and Paul, who's been doing this for a long time. So I think that might be useful in the future. So someone's written here, how do you practice? Oh no, sorry. Do you use incremental problem solving?
as recommended by Piotr,
Mm.
I'm not sure what's incremental problem solving.
I think it's just having a problem and, you know, maybe you work on it on Friday and then next week you don't really think about it at all. And then you come back to it and maybe you make a little bit more progress, an incremental bit of progress. And then you come back a month later and you realize that you've thought of something in that in-between time that can help you solve it. So it's like you just slowly solve it over time. Do you ever do that?
Um, I think that's how we solve all problems,
Mm.
but that I think even normal mathematicians do that all the time, where they start with a theorem, and in the beginning it's super complicated, and even them, they find simplification. It's just that they don't have to go as far as space repetition practitioners have to go.
Mm.
So I think that's the only way to solve problems.
Interesting. Oh, yes, there's a really good question here. Have you made any connections or solved any problems in your work as a mathematician that you directly attribute to your use of SRS?
Yes, my own thesis.
Your own thesis. Brilliant.
Yeah,
Is it?
I mean that I did a lot of theorem abstraction inside the thesis, where I was trying to find the more general statement, and I think the only way to reach the ultimate abstraction was with the space repetition and remembering all these abstractions.
Oh, amazing. Have you got like a good problem solving story of maybe that involves you looking through your space repetition or doing your repetitions and realizing that there's some theorem that you can use that you never thought of, or something like that, some serendipitous connection that you've made?
This happened all the time, but it's never. But because it's so incremental, it doesn't make a good story.
Okay.
Like, oh yes, I made a teeny bit of progress today. I removed 2 lines of a proof. It's just, but my own thesis is a bit about that. It started as something super ugly, and it got more and more beautiful over time.
Very
But
nice.
there was no. Uh, there were several steps that made it more and more beautiful. So I can't say, oh, at that moment everything got super beautiful. Of course not. We're believers in incremental progress. So at that moment things were a little bit more beautiful.
I was hoping for something akin to, Newton sitting under the tree and the apple falls on his head. But I suppose in most cases it's
That's
going
just
to
a
be,
story.
yeah, it's just a story. I suppose in most cases it is actually very difficult to record a creative process because everything does happen so incrementally. You might be recording and like showing that progress over such a long period of time that it's not really obvious. There's no sudden realization or anything like that. Okay. I forgot to ask you. There was something you mentioned in the last talk you did. Something about how like 50% or more of the new knowledge that you add into the spaced repetition system is just generated based on stuff that you've already got in there. Can you talk about that process?
Well, one thing that often happens is that you have a statement that in a and you realize the statement can be abstracted. Uh, Let me give a very simple proof, a very simple statement. In group theory, you can prove that the uh, the neutral element is unique. But it turned out that this proof is also true in monoid theory, where you don't use all the full axioms of group theory. So that was one of my earliest realization when I was doing space repetition. I had
Mm.
memorized the context, so I had to say the one is unique in what structure, and I said the group. But because I remembered the proof, I told myself, wait a minute, I don't use the inverse, so it's valid in the monoid. And that was when I discovered for the first time that when you use space repetition, because I knew every step of the proof, I knew which hypotheses were used, and it made it very easy to remove unnecessary hypotheses. So part of the process is just trimming your theorems by removing any kind of unnecessary hypothesis. And it's easy to do the more and more abstraction and structure you know, and the more you know your proof because you know which hypothesis is used or not. And perhaps in my case, the most amazing one was when I started abstracting my proofs of linear algebra over and over and over, and I discovered a lot of proof of matter theory, which is an abstraction of linear algebra, just by making more and more abstract proofs. And at some point, I learned that someone had already done all the work, but it was really magical that the process happened so naturally. And I think any user of space repetitions will come at many similar abstractions. So it's not a so that's an example, but there's also the fact that sometimes you generate hypotheses from your knowledge. Like there's an idea you think might it be true or not, and then you start proving it, and it's easier to prove because you have all the knowledge inside your head. You don't need to look at as much into books because to prove a new idea or to generate a new idea, it's much easier when the knowledge is inside you.
Yeah, that's awesome. That's like very motivating for me as someone who's starting out learning mathematics. That sounds like such a fascinating and interesting process. It sounds very similar almost to, I guess that it's similar to incremental writing in a way. It's like, I don't know, it just changes the way I think about math in a way that makes it seem much more exciting. Like that incremental abstraction, you're creating something. It's a very creative process and not just, I don't know, memorizing theorems. It's very interesting. And so, in your day-to-day sort of in your day-to-day studying, how much time do you spend doing repetitions versus reformulating and doing that incremental abstraction that you talked about?
I would say I spend the it's a I would say 50-50, but maybe the numbers are wrong. It's hard for me to give an estimation, but I spend a lot of time reformulating. I found out in the beginning that if you don't reformulate, all you'll have is leeches.
Mm.
And we're not trying to memorize a phone book. We're trying to memorize very deep and abstract theorem. So reformulating over and over and over is the result of learning deeper abstraction and more theorems and of having more and more ability to prove things. As you keep reformulating, theorems become more and more beautiful.
Very nice. Okay. How would you tackle a new textbook you wanted to digest? For example, introductory linear algebra. How do you decide what's worth remembering and what's not?
Okay, so I gave up textbooks years ago. I started by tackling textbooks, but the problem with that is that often they don't have the best proof. Um, So at this point, I'm much more incremental. I I learn theorems at the à la carte, one by one,
Yeah.
rather than a whole book. So at this point, I just want a specific theorem. I might look in a textbook and look for a theorem. So I would not recommend tackling a whole textbook because it suffers from many problems. One of the problems is that all textbooks strive to be self-contained, and because of that, the proofs tend to be very ugly and more complicated than the most general proof that we'll find on Wikipedia. And
Okay. So
the
so you're just going to the theorem buffet and picking out what you want.
Yeah, at this point, yes, and I find this way more exciting than looking at a book that might have a variety of theorems I might care about or not about. So I go with the theorems that I care about the most, rather than a list already made by someone else. I don't follow a curriculum anymore, so
Okay. So is your decision about what's worth remembering just entirely based on interest? Just what you find
uh,
interesting?
so yeah. At this point, yes, I no longer need a diploma. I do things just for my own pleasure. So there's no I don't like being forced to memorize things.
Mm. Do you have any recommendations or any advice for people who are in university or school and they're studying mathematics?
Um, so I spoke with one user here that use space repetition during his course, and he told me that it made him hate space repetitions. So I really wish I had recommendations, but I don't because school is not very optimal for learning.
Mm.
At school, there is too much material that is being shown during a given day, and it's too much that space repetition is not able to tackle that huge quantity. While I'm willing to say that it's miraculous and super efficient, uh, even with the full power of space repetition, it would not be possible to learn at the speed that school demand. So, what are my recommendations for people at school? Cram and dump until you have your diploma, and then you can learn mathematics for pleasure afterward. And yeah,
Okay. Um, oh yeah, here's a good question from Deep Blue. What cues you to, or what do you notice is wrong about a flashcard, or what do you notice? I'm not saying this right, but what causes you to want to reformulate something? Is it like answering a close and you get it wrong, or do you answer a close and you realize there's an abstraction you could make, or do you actually search to manually reformulate them, or how do you go about it?
okay. So anytime I notice a new abstraction, I reformulate automatically.
Okay.
And then at anytime I notice an improvement, I reformulate. So this is cued by just seeing an improvement to improve. Anytime I think I have a new idea, I always want to incorporate it. And there's another thing that cues a reformulation. It's when I have a leash. A leash is just a card I've badly formulated. And how do I know it's a leash? Well, if it gives you a headache to answer something, it's a leash.
Mm. What part of maths do you enjoy the most? Is it doing your repetitions, doing the reformulation, or working on a problem with pen and paper? Which is like the most pleasurable for you?
They're all pleasurable.
Okay, all of them.
Yeah. Well, there are things that are taxing. I find often reformulation to be very taxing.
Mm.
If it's like a bad leash, uh, having to find out the right formulation might take a lot of mental effort, and there are days where I feel tired of with that. I but I'm very satisfied with the result afterward. Like when your collection is very beautiful and uh, every flashcard. But maybe part of the pleasure is just when I think naturally about mathematics and to have all uh, these things inside me. I, every time I make a new association, it gives me a lot of pleasure.
Very nice. Okay, if textbooks aren't good, how would you recommend starting to learn maths for a beginner?
Um, that's a. I, in my case, I start with a. I guess you could start with a question that interests you. For example, in your case, you said, for example, I want to learn algebra, and
Mhm.
you realize to learn algebra, I need to learn set theory, and then you realize that to understand set theory, you need to learn logic. So
Exactly.
just by having a specific question in mind, there's already an immense list of knowledge that you need to incorporate and learn, and eventually you will have learned some logic, some set theory, some algebra, and you will be able to generate new interesting questions, and you're already ready to start toward the infinity.
Yes, yes. I'll give my advice. Obviously, I'm just starting out, but uh, probably for maybe a year and a half, uh, I've just been reading about the history of mathematics and a little bit about the philosophy as well, and especially focusing on like the main characters in mathematical history. I'm especially interested in the foundations of mathematics. So like Kurt Gödel comes up a lot, Georg Cantor for set theory and stuff like that. And they all have, oh, and Turing, of course, as well. And they all just have such fascinating stories behind them. And obviously the problems that they solved or ran into, the paradoxes, they became so influential now, even today, like hundreds of years later. So yeah, that's my recommendation is just start with the kind of fluffy stuff like the history and a little bit of the philosophy as well. And there's loads of documentaries on YouTube that you can watch that will immediately, I guarantee that will get you like a little bit of interest pumped up, because I mean, like I hated math in school and I really had bad associations with it. But just by easing my way in and learning about that sort of oh, you've got Russell's paradox in there. Nice. Yeah, just easing my way in, I found that to be a very effective method of becoming more enthusiastic and motivated to learn mathematics.
I think school is not good um, for learning mathematics.
Oh, it's not good for learning anything. It's terrible. Yeah.
Yeah.
um oh yes, how much time do you spend in your SRS software each day, and is it like consistently the same amount of time, or does it vary day to day?
That's very day to day. For example, when I have a deadline, I just do my repetition and I don't try to add new theorems. And there are days where I have nothing to do but this. If I have lots of free time, I might spend 8 hours. If I don't have a lot of time, I just do the repetition, and it might be half an hour some days. So it's hard to give a very consistent number. And I just want to mention that I too have been very touched by Russell and Cantor.
Mm. Yeah, yeah. I really find that fascinating, the especially the paradoxes, because you can understand the paradoxes in like natural language. It makes sense because you can see that there's a contradiction. And then when you realize that, for example, like mathematics is supposed to be error free, and you wonder about the implications of that, it makes it interesting, and you can understand that rationally without knowing any math, really. So yeah, I really recommend actually like maybe read up about Russell's paradox and why it's important and the philosophy behind it, and I guarantee that will get you interested in learning more about mathematics. Oh, there's another good question here. Yes, do you read material and immediately think of formulating it into a card, or do you sit once to gain familiarity and then come back later to reformulate it as a flashcard?
It depends. Someday you see something and it's so beautiful that you want to make a flashcard of it. And at other times, yes, you gain familiarity, and then you think, okay, this would make a good card. I think it's like that for everyone, even if you're not a mathematician, but you're using space repetition system. Both things will happen to you.
Mm. Okay. Has anyone else got any questions that they want to add? I think we're at around an hour and 5 minutes. So yeah, let me know if you have any final questions. I'll ask my final question. I had a final question. I've forgotten what it was now. Um, I've remembered my question. Okay. Okay. So why do you think that spaced repetition isn't commonly used for mathematics? It seems like you've uh, benefited so much from it. You mentioned that you have theorems and proofs at the tip of your fingers and so on. So why do you think it's not really talked about or not used widely?
Um, so I think the knowledge is just not there yet, but at some point it will be there. There, I hope that by doing a video like this one, there will be more people. But it's something that is growing exponentially already. So I think it's just not used because people don't know. But more and more people are knowing. People are adopting it, and it always takes time for a new method to get through. And another reason it might not be used much is that the current learning method school is not that compatible with it.
Mm,
And it's going to be people that want to do it and perhaps in my case no longer need the diploma because they already have it or don't need it because in their field the diploma is not that necessary. Uh, but I'm confident that one day most mathematicians will use spaced repetitions.
very interesting. Yeah. I'm really interested to see how it develops over time, whether you'll see the sorts of like exponential adoption that it's seen in other fields like language learning and some other areas like I guess medicine students use it as well. But
But
yeah.
let me say there's a difference with language learning. The difference is that it's much harder to formulate properly
Mm,
with math. In math, formulation skills are much more complex. There are other people that I find very very smart and very good in this chat room, and for perhaps they lack a little bit of knowledge for being able to do the proper formulation, but I or perhaps they lack encouragement, but I'm convinced that everyone who want to learn it can learn it. It's just the the step are higher.
interesting. Okay. Well, I think that pretty much rounds it off. There are a ton of questions that I didn't get to, but I don't want to stretch this on too long. I don't want to exhaust Paul. He's got repetitions to do. So I'm going to call it here, and we can definitely do more of these in the future. Paul, you mentioned that you'd at least for a bit you're free of deadlines, so um,
Yes,
there are still way more questions, and if I didn't get to it this time, I will definitely try and ask it next time. Um, yeah, so I think that's it. Paul, thanks so much for giving your time, by the way. It's always great to hear you talk about this stuff. It's just fascinating.
my pleasure.
All right. Thanks, guys, for showing up. And thanks for all the awesome questions. And I'll see you next time.